Hi there, this is Jacob Nash, and welcome back to Physics with Nash. This is going to be lesson 3. So, one thing that I wanted to say before we start this video is in some of these presentations, I'm going to be using some images from the textbook Mastering Physics, which is also the course line that I base these videos off of. So I just want to put that out there that I'm not taking credit for some of these images in here. All right, so this video is just going to really briefly talk about a few different concepts, but I also want to say that these are just concept reviews. And I will have a separate video here soon, multiple videos where I actually work through problems relating to these concepts. So that's the thing. It's like a two-prong factor for these lessons. You got to know the concepts and how to apply them. But the second thing, how to apply them, is a lot more time consuming. But we'll look at some of those later on. But we're going to talk about first uniform motion. So all this means if an object is in uniform motion, it just simply means that the velocity is constant. So how would that look graphically? That's really important for us in this class is to know how things would look graphically. Um, and if you see here displacement versus time graph, it's going to have a constant slope. That's what indicates that the velocity is not changing, which is why it's constant. And you can see equal displacements as you go up a certain length of time. That's what that means. But non-uniform motion is if there's not a constant velocity, so anything else. And of course, this is more common. I mean, oftentimes that's not what we have. But it's just important to know what that means if you hear that. Now, what about if we have constant acceleration? What would that look like graphically? Well, if we had a velocity versus time graph, it's going to be if there's a constant slope for that, because the slope of this graph is going to be our acceleration. So if it's the same slope as we go, this example is showing two different graphs, one of acceleration or velocity versus time of Porsche and then Volkswagen. But for both of these, the slope is the same. It's just a line. So that's what tells us that there's constant acceleration. If instead it was like curved, that would mean no, it's not constant acceleration, it's changing. And if it was just a flat line, then we might say that it has zero acceleration. All right. And an important skill, you're going to want to know how to convert between the S versus T, V versus T, and A versus T graphs. So what is S? I haven't really talked about that. Well, that actually means displacement. And so you might be thinking, I thought we used X. Well, displacement can occur in either the X or the Y direction. So if we just use the letter S instead, that sometimes is more useful for a description such as this. That way I don't have to say X and T and Y and T. So S versus T just tells us displacement versus time, but we don't necessarily know what direction that might be. But right now we're just thinking linearly. So there's only going to be X and Y direction right now. And we can just represent, if we're talking about both of them in general, we can use the letter S. But anyways, you want to know how to convert between these three graphs. Now, I've already made some AP Physics videos on this channel before, and we've talked about that in terms of if you do the slope or the area under the curve. That is exactly how you can convert between these. So the slope of this graph gives you this graph. The slope of this graph gives you this graph. And to get back, area under the curve this way, area under the curve. Now, in case you don't know what that means, I'm just going to explain that because I do realize that you can skip this if you do know what this means. But um, hopefully you've taken calculus or something that you would know what these things mean. But I'll show you first, slope, of course, going to briefly talk about it just because I assume you probably know what it is. But so, like I said, the slope of this graph is going to help us construct this graph if we needed to draw it, or choose it from a multiple choice. So to find the slope, it's going to be how much it rises over how much it runs, rise over run. And whatever that is, well, this is a flat line. So whatever that tells us that every time you're going to get that same number for rise over run. And whatever that number is, we would just, when we go over to the velocity versus time graph, let's just say it was up 4 over 2. And the slope is 2. So then to make this graph, you just do this. It's going to be flat because uh, it's constant slope, that means constant velocity, so it's always 2. It would be different though if it was like that. Then it would be a little bit harder to draw with exact accuracy, but you might say then it would look like that. Um, so that's how slope goes. The same thing is true if you want to go from velocity to acceleration. But if we're trying to go the opposite way, so let's say we have, we'll just say velocity over time that looks like this, then how are we going to get over to this? X versus t, which by the way, it could be y versus t or s versus t. But how do we, well, we do the area under the curve. And what that means is we split this up into shapes. Eh, yeah, so probably the best way to do it would be this. So in this case, so we have three shapes, and you just find the area of these three shapes. So whatever the value it is at this point, you say that's the length times the height divided by 2 for the triangle, and then just length times height for these. And that that's going to tell you the area under the curve, and you can use that to apply to this over here. We're going to look at some examples with actual numbers in the other video, like I said, but just as a general idea, that's what you can do. Now, slope and area under the curve can also be, you don't only have to do it graphically. If you feel like doing it um, in terms of calculus, if you take a derivative of a function, that is the same thing as finding the slope. And if you take the integral of a function, that's the same thing as area under the curve. So that's also something that you can do. So now, here are some three equations, kinematic equations. That is what we're talking about, kinematics right now. And really, when we're talking about kinematics in a general sense, we're just talking about an object moving relatively linearly, but in this case, with a constant acceleration. So our acceleration is never going to be changing. It's either going to be the same value or zero with these kinematic equations. Um, these three equations would be very useful to memorize, but check with your specific situation whether or not you have to. You might be able to just have a formula sheet, but it's also just good to remember these. So if you've taken AP Physics before, you probably remember these. The only difference is that maybe if you even happen to watch my videos on this channel from a few years ago, I might have not used these exact subscripts, um, I and F. Maybe I used 0 and F. But it means the same thing. The subscript of I means initial, and the subscript of F means final. So final velocity, initial velocity. So they look kind of crazy, I will say that, but they're really not that bad because all that happens where you use these is that you're going to have a problem and it's going to tell you it's a word problem. They're going to tell you a few things and you're going to write using the process that I've said before. You're going to write what you know, what you need to find, draw a picture of it, equations, think of the equation that you'll use using what you know. So if it wants you to find acceleration and it told you time and velocity, you just plug in those values to find A. Um, and that's the same for these other ones. So the one that looks probably the stupidest to you is this green one. It's a little bit crazy, I realize, but it's really not that bad. You might just get thrown off by this 1/2 squared. Now, I will say something about these equations. It doesn't really matter technically for you to know this, but in case you're interested in how these actually come, they actually are derived from the more simple equations that we know, and they're derived from derivatives and integrals, and that might make sense if you think about it. Why would there be a 1/2 square n squared? Isn't that something that happens sometimes if you take an integral? So that might make sense to you in a way of how it gets to this. And there's a whole process that you could do if you wanted to do that, but you don't have to for this course. Um, but anyways, the blue one is one that you have to be careful about. Well, I guess this one too, because of the squared, but you have to be careful. Obviously, if you take the square root, if you're trying to find t, you would know that you're not going to have a negative time. But for the blue one, you have to be careful because if you are taking the square root to find one of these, you get a positive and negative number. That's what happens when we take a square root. And you have to choose based on what makes sense for the problem, whether you'll choose the negative or positive one. And that depends on what direction you're supposed to be going in. So that's something to think about there. So we'll come back to these when we look at examples. All right, last thing I'm going to talk about just quickly is free fall. So if an object is in free fall, then we are saying that it's only affected by gravity. In the real world, this doesn't happen because we have air resistance. And in AP physics, we don't even talk about that. Um, if you never took that class, then disregard what I'm saying. But we didn't care about that in AP Physics, at least AP Physics 1 that I've made these videos on before. We never cared about that. And for now, in this class, we also aren't going to care about air resistance right now. But if there's only gravity acting upon the object, then it's in free fall as it falls. And the acceleration from free fall is 9.8 meters per second squared, approximately. Later on in the course, we'll figure out how to calculate that or how that is calculated because it would be different for other planets. And you might know that already. It involves that big G, if you remember that gravitational constant. Um, if you don't know what that is, just don't worry about that then. We'll talk about that later. But the magnitude of this acceleration we represent with a lowercase g, not uppercase g, because as I mentioned, there's something else that is a different constant that is uppercase g. So we use a lowercase g if we're talking about that. So if you had a question like this, a ball is thrown vertically upwards at a speed of 10 meters per second. At the moment that it reaches its maximum position, what is acceleration? Well, basically, you know when it's at its maximum position, the velocity is zero. That makes sense that its speed is zero, but obviously velocity and speed aren't the same thing. But if you think about it that way, it does come to a stop. So you can think of it as that way, that the velocity, in fact, is zero at that moment when it's at its highest place. But is the acceleration zero? No, that's not going to happen because gravity is going to always exist no matter what. So as far as something that goes in a vertical direction, the acceleration in the y direction can never be zero. At least on Earth, that's not a thing, but there can be. It's always 9.8. Now, air resistance can make things a little bit different, but if we're just assuming that it's in free fall, the answer to this question is that it's still going to be 9.8. It always will be. But we would actually say negative because it's actually acting in the negative direction. So that's important. It's going to be negative 9.8 because since the force of gravity is pointing down, that's what's going to be. And we will learn more about that, F equals ma later on. Um, newtons. So anyways, that's going to be all for this video. Thank you for watching.